What if our characteristic equation has two complex roots? What are we going to do? Okay, now, in this video, what I plan on doing is going through where the solutions come from, but in the end, there's going to be a formula, okay? So if you want to fast forward to the end and see it, then I suppose you can. But I plan on going through exactly how to get those, okay? So this one's going to be very tedious, but when we are all done, it will be shorter than I make this right now, okay? The first thing to talk about is Euler's formula. Now, maybe you've seen this, maybe you haven't. Just in case you haven't, here we go. So e to the I theta is equal to cos theta plus I sine theta. If you'd like to see a proof of this in my 5B class, I usually prove this using series, which is really kind of fun. And I think I might put that in an appendix in these notes for later use. If you haven't seen that, go look it up, but there it is. So e to the I theta equals cos theta plus I sine theta, and we're going to use Euler's formula here in this problem. All right, now let's get to it here. Suppose I have y prime plus y double prime plus 4y prime plus 5y equals 0. Okay, now as a note, I want my solutions y to have real coefficients, okay, like our original equation, and we're going to be able to find those, okay? So I don't want to stop where I have e to the, ix. That's not going to be okay. I want to go all the way until I am done, all right? So here we go. What do I know? I know that my characteristic equation is lambda squared plus 4 lambda plus 5 equals 0. And that means that lambda is going to be negative b plus or minus square root b squared minus 4ac all over 2a. If you would like to sing the song, go right ahead. I'm not going to. Plus or minus. All right, 16 minus 20 is negative 4, which is negative 2 plus or minus 2i. Which is over 2, negative 1 plus or minus I. All right, so here are my lambdas. Very good. Now, what does that give me? That gives me y1 equals e to the negative 1 plus I x, and y2 is e to the negative 1 minus I x. Okay. Well, what is that? This one is e to the negative 1x plus ix, which is y equals e to the negative x times e to the ix. Yeah? And in a similar way, y2 is e to the negative x e to the minus ix. Now I'm going to change this. I'm going to change this thing using Euler's formula from up there. So in this problem here, what I have is theta is x here, right? So this just turns into y1 is equal to e to the minus x times cos x plus I sine x. And I'll go ahead and distribute that. So 1 is e to the minus x cos x plus I times e to the minus x sine x. All right, there's my first function. That at least has some stuff I can deal with well there. For y2, my theta is minus x, right? Okay. So for y2, I have e to the minus x cos minus x plus I sine minus x. Now let's pull out our trig skills here. So cosine is an even function and sine is an odd function. So let's do two things at once. That's e to the minus x cos of positive x minus I times e to the minus x sine of positive x. Okay. So there is y2. Now remember where this problem started. I want to have solutions with real coefficients. I want that thing gone. This is bad. So watch this. Let's call a new function y1 with a little hat above it maybe. And let's do y1 plus y2 divided by 2. Okay, well, what do I get when I add those things together? Well, when I add y1 and y2, these cancel, right? Because they have opposite signs. I'm not going to leave those canceled, but that's the idea. And then this other part, I get double of. So this is 2e to the minus x cos x, which is just e to the minus x cos x. And y2 hat, let's do y1 minus y2, and let's divide that by 2i. Okay, again, remember that linear combinations of functions of solutions are still solutions. So I know this is going to be a solution. Let's try this one here. So if I do y1 minus y2, that means that the coses are going to cancel. That sign's going to flip, and so we'll add them. So that means that we're going to get 2i e to the minus x sine x over 2i, which is just e to the minus x sine x. Okay, now, fact, feel free to check it, y1 hat and y2 hat are solutions. Okay, and they're also linearly independent. Okay, I've run out of paper here to show you. And so what does that mean? That means that the general solution is, in fact, linear combinations of these two things. And so the general solution is a e to the minus x cos x plus b e to the minus x sine x. And note that that didn't have any i's in it. Okay, so I took linear combinations of all the stuff. I messed with these ones that had i's in them using Euler's formula, and I got things that didn't have i's in them anymore. Now, hopefully that made sense, and I showed you where that came from, because I am going to give you a formula on the next page. So on the next page, we can generalize like this. Okay? If lambda equals alpha plus or minus beta I are solutions to the characteristic equation, then the general solution to the differential equation is y equals, and there's two ways to write it, e to the alpha x times a cos beta x plus b sine beta x. If you'd prefer to use different letters than a and b, if you want to use c1, c2, then fine. Or you can write it like this: a e to the alpha x cos beta x plus b e to the alpha x sine beta x. All right. Now you can follow our example from before now with this formula in mind, and it totally works. Why don't we do one just skipping right to using the formula? Okay. Now this, again, don't make this a hard thing. This is an easy thing. All right. So here we go. Example 175. The characteristic equation is lambda squared plus lambda plus 1 equals 0. And so what do I get? I get lambda equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Right, so I get negative 1 plus or minus 1 minus 4 is negative 3, so that's root negative 3 over 2. I feel like I've missed a number here. Alright, looks good. So I get lambda equals negative 1/2 plus or minus I times root 3 over 2. Okay, so I'm done. This is alpha, this is beta. the general solution is e to the negative 1/2 x times a cos root 3 over 2 x plus b sine root 3 over 2 x. All right, so please don't make this something super difficult. All you have to do is find the characteristic equation and solve. Okay, let's do another one. So characteristic, lambda squared minus 6 lambda minus 2 equals 0. So lambda equals negative b plus or minus b squared minus 4 times a times c all over 2a, which is 6 plus or minus 36 plus 8 is 44, I think. Now, what do you notice here? That is going to be 6 plus or minus 2 root 11 over 2. So lambda is going to be 3 plus or minus root 11. What kind of root is that? Is that real or complex? Now, it's real, it's not complex, and so this doesn't fit this kind. The general solution here is a e to the 3 plus root 11 x plus b e to the 3 minus root 11 x. And that's done. So be careful. I know this kind of has the form of the complex kind, but it's definitely the real kind. All right, I know that was kind of lengthy in explanation, but make sure that you sort of boil it down to knowing that these are easier than they look. In the next video, we will talk about what happens in the repeated root case. All right, I'll see you then.